Welcome to this week's episode of the Foresting Tomorrow podcast. And this week we have a special guy on air. It's Max Pramreiter. Is that pronounced
Yeah,
correct,
I would say
Max?
that's.
Or actually Maximilian, right?
Yeah, you can say Max as well.
Yeah, that's what I read on
Mm.
LinkedIn. So you go by the name of Max now.
Yeah, it's shorter, so it's easier.
So Max, yeah, you're a senior scientist at BOKU University, right?
Yeah,
And
mhm.
also a host of the WoodCAST podcast. So you're a fellow podcast host.
Yeah, that's true, and I think it's the second time that I switched places from asking questions to trying to answer them. So I'm really thank you guys for the
Ah,
opportunity to give this a try again. Um, and yeah, I'm with Boko for 7 years now. Yeah.
okay. So how's your history into the whole world of science and wood and everything?
So the history of getting into wood started pretty early, I would say. So from a family background, we don't have any company background or carpenter background or anything. So my parents were um, have nothing to do with the material itself. But in Austria, there is a certain time when you're like 14 years old, you have to decide which kind of school you're attending. And there are
Yeah.
always these big fairs where schools battle for attention, I would say. And this school
Hmm.
had a wooden bike frame as as eye catcher basically. And this drew my
Okay.
attention immediately, and I checked it out, and it was the higher technical college in Salzburg in Kuchl, which is um, basically one of two schools that offers wood technology as main focus of their school itself. And it's funded in part by the industry to create people for the wood industry in Austria, which is a pretty big industry, I would say, also considering
Hmm.
the high share of forest coverage. So I attended this, and this was 5 years. And then there was the big question: should I move into industry or should I go to university? And then two of our teachers were alumni from BOKU as well, and they said, "Okay, check this out, and maybe you could give this a try to go to BOKU to
Hmm.
do wood technology as your bachelor." Um, and I always wanted to move into a city at one time in my life because I grew up on the countryside. And Vienna is actually a pretty nice city to live in. So I think this was a help in the decision to move to university. And then it happened organically, I would say. So there were a few steps where the question moving into industry came up again, but always when this question was raised, there was a really interesting topic in regards to either the bachelor thesis, the master thesis, so in regards to research. And this is
Yeah.
how I basically drifted from going into industry, which was a big focus of the school back then, to stay at the
Yeah.
university and go into science. Um,
Okay.
so that's basically how it happened, and that's why I'm still here at Boku, because I think the topics that are covered are uh, interesting and important.
Yeah. This wooden bike frame that you saw was it the fascination about wood being used in this way, or that it could be done, or what was that sort of caught your attention?
Um, I think it was on the one side that it looked natural in a way compared to all the I would not say synthetic, like purely synthetic bike frames. So it just looked like it just looked nice, which is interesting. If you're 14 years old, you're not so much into the details of production processes or strength to weight ratios or anything. Um, and then, so this drew the attention, and this was the main. So I wasn't that much into bike riding. It was just how it looked, actually. Yeah.
Yeah, okay. But that aligns pretty well when we have discussed the buildings in wood and
Yeah.
material like that. Why are we fascinated about it? It's just because it looks nice. It feels nice and looks nice.
Yeah.
So there's just something about wood that gives you that feeling, even when you're 41.
I think
Yeah,
I
so,
think
yeah.
it's not age dependent to have this
No,
nice
no, no,
feeling
no, no.
about
It's
wood. Yeah.
It must be something that lies deep inside us that we like it.
I would say it has to do with the natural, so the renewable nature and the natural nature about it. We come from living outside and outdoors and
Yeah.
building shelter with wood basically, and I think this is one of the main reasons why we are drawn to it. Um,
Yeah.
and it's unfortunate to see how
I
much it's covered up right now in most of the buildings.
agree. Yeah, you're right. You're right. What was the what was the first? Normally, I remember. Actually, Rasmus and I, we studied together on electronic systems. I think it's called.
Mm.
So it's a mix of electronics and IT. And I always remember some of those first projects that we worked on. When we just started out on the bachelor. What's sort of your best memories of projects that you have worked on in the early days
Mhm.
in the university?
Mm. I think it was pretty fortunate to do my bachelor thesis. So I did it in 2015, I guess. And
Mhm.
back then there was this. Uh, so we talked about hype words and buzzwords before. So
Yeah.
back then there was this hype word, or it still is, of Industry 4.0.
Ah,
Yeah,
yeah.
and one of my teachers basically had this idea, or basically had this vision of making wood uh, predictable in order to use it in the automotive industry. Um,
Predictable. What do you mean
like
by
using
predictable?
finite element modeling and material characterization to allow it to be used as high performance material in the automotive industry. So that was basically the vision and the idea behind it. And back then,
Yeah.
this meant you need to be able to implement it into the way the automotive industry does product development. And the product development in automotive industry is mainly done used computers, and then just a selection of actual tests
Mm.
compared to, and this, so there is no, so I would not rank those two approaches, but in some parts of the wood industry, it's still trial and error. So you do a lot of laboratory experiments to gain
Mm.
insights into relationships, which is a totally fine way to do, but it's not feasible in automotive construction because it's just too expensive. So
But
and yeah,
is it? No, sorry.
sorry.
Just keep going. I'll ask afterwards.
um, so yeah, this was the main vision for it. The reason for that was that the basically all the reasoning is based on climate change in research, I would say right now. But the specific area this came down to was the fuel consumption of cars is driven by their
Mm.
weight. Um,
Mm.
and here we could see, or here we can see that wood has one of the best strength to weight relations out there, and therefore it would be possible to decrease the weight of a car without decreasing the safety issues and the comfort issues and the basic necessities that are needed to in order to create a car for um, on a mass scale as well. Um,
Mm.
and this was one of the first things that I did in my bachelor studies, to work on these first tests. I would not call it prototypes because it was not actually something that could drive on the street, but components of cars that we tested and how to produce them and which wood material to use. And this was really interesting because, um, as far as the story goes, it was always said it's not possible to do that. Um, but as it turned out, in general, it's possible. Yeah? I mean, there is still a long way. I would not say a long way, but there are still some
There's
challenges
still
to
work to be done.
overcome 10 years later. But now they are far closer to realizing that than they were 10 years ago. Yeah.
What kind of components in the car
Mm.
could actually be replaced by wood?
Um, So first, I would like to mention Ulrich Müller, who was the head of the project and the head of this vision, in case somebody wants to check out more details on it.
Nice.
It's always important, I think, to mention this. So in regards to components, we looked at different parts of a car based on actually how difficult it would be to replace it. And one was the so-called side impact beam, which is in the door frame
Yeah.
of a car. And
Yeah.
typically how the car industry and also how the professors are usually explaining it is, it's something you hope you don't need, but in case you need it, you're happy that it is there because it's supposed to save you if you're in a crash, and it's supposed to have a high first impact strength, and then it should take up a lot of energy through
Yeah.
deformation without breaking. So
Yeah.
it's two actually not well fitting together aspects that need to be
Mhm.
combined there. So this was basically selected because it's one of the most challenging components that you can build or that you can create out of for a car, out of whatever material you might choose.
Yeah.
And as far as the results go, I think it was possible to have the same amount of energy uh, uptake uh,
Mhm.
with 2/3 of the weight, basically. Um,
Okay.
so this was one of the outcomes by combining not only solid wood but basically wood-based materials with still synthetic adhesives. I think that's always something important to mention here, that it's not this
Yeah.
100% nature-based solution which is available right now, which is also something that the wood industry or basically the research on natural materials has to be honest about, I would say.
Mhm.
But this was one of the components that was most interesting, I would assume, because also seeing the actual crash test that was done afterwards just reminds us or just underlines how important it is to do this stuff on the computer, because one test is crazy expensive. Yeah.
Yeah.
Mm.
Yeah, that's actually my question. Why is it that isn't it possible to adopt the methods from using, steel, using this model-based approach instead of trial and error with the
Mm.
wood materials? Is it
Mm.
because it's so hard to model, or is it
Yeah. So
simply that it has?
mm, so the approaches would be the same as for steel or glass fiber components or whatever kind of composite material you would use. However, as wood is a natural material, there is two sides to it. One is the variability of the properties, which is something that has to be dealt with also in timber construction, for example. Yeah. The
Mm,
second part is the uh, directionality of the properties. So in one direction, it has different properties than to 90 degrees to it, for example. So the anisotropy
mm,
of the material. And also that there is or was little knowledge about the behavior during break. So
mm,
how to model actually this failure process. And here, the Technical University of Graz has built up a lot of expertise as cooperating partner in this, in how to actually model this. And this is something where the basic tools or the basic softwares are similar as for the steel or other composite material modeling, but the expertise was not there to use wood here. So it's mainly these components that needed to be improved here, yeah. And where it was always said that it's not possible because it's too complex compared to steel, for example.
mm.
Mm.
Yeah, okay. Yeah, because the material is just less complex.
Mm.
Steel is less complex than wood. Yeah,
I,
makes sense somehow.
let's
Okay, maybe I'm I don't,
let's hope that nobody from steel research hears that, because I think they would
yeah,
disagree
yeah.
here
You
as
can
well.
see
But
that I
um, but
made a simplification there.
yeah, but I think here what I think needs to be mentioned is also the amount of time spent actually perfecting
Yeah.
steel components and steel in different kinds
Mhm.
of whatever material use you might think of over the last 100, 120 years. So I think this is one of the main reasons that they are way further in understanding the complexity of steel on a different level, of course. Yeah.
Yeah, that makes sense for all industries. That's also, we have gasoline-driven
Mm,
cars for so many years, but now it's being slowly overtaken by electrical.
mm,
Uh, so that's also why electrical cars will be there for many years because it's so hard to shift again
mm,
now.
mm. Yeah,
I don't know
totally
if
the
that's coming
same.
in here.
The
Yeah,
same reasoning. Yeah.
yeah. But do you, like, for instance, like with the use cases of using steel, like you have military components, you have Formula One cars, you have aviation, you have a lot of industries like really specific where the amount of resources spent on investigating the properties of these materials. Do you have anything similar in the uses of wood where it's taken to the extreme level of what it actually can do?
I mean, the extreme level, as you mentioned, Formula One cars and planes, I would say that we
Yeah,
have had the time in history where wood was used for these things. I mean, there's still an
yeah,
English company producing race cars out of wood, using wood for the frame. Um, I mean, I would not assume that it would win Formula One races, but I would assume that if you would bring wood back into Formula One, um, it could be used. But I think that the education and the tools that are available for these teams and for these development teams is geared so much towards glass fiber composites, for example, or other composite
mm,
materials that are not using natural materials, that it was just lost over time. Also, considering wood was
yeah,
used in airplanes at the beginning pretty efficiently, also during the
yeah,
World War. So I think we
yeah,
have been there in the past and we just lost it. Or like shifted focus, I would say.
yeah.
Um,
You're probably right.
and I think one example I wrote down was one of my colleagues is working a lot on wood in historic uses. So you can
Okay.
check him out, Michael Grabner. He is spending a lot of time investigating how wood was used in the past, and he has some really interesting presentations on that. And for example, he always brings a researcher from 1917 who investigated different buildings and stuff. And back then,
Okay.
they found 27 different wood species in just one building, which we would compare to
Wow.
today, it would just be a handful, I guess. So
Yeah.
there was this knowledge of using different wood species for each specific purpose. Um,
Yeah.
yeah, just as a side note on this.
That's funny.
That's really interesting.
Yeah.
Yeah.
So I guess that was yeah. So that was your bachelor.
A
What
bachelor
about
and PhD, actually. Yeah.
okay.
Yeah.
Yeah. So let's talk about more about your PhD and also the work that you're doing now.
Mhm. Um, so yeah, with that, actually, my bachelor and my PhD topic was focusing on this wood for high performance applications. Actually, during the
Okay.
PhD, um, you for the first time you realize that you have to decide on a specific question or a specific topic out of this whole universe of wood, um, and you get even narrower focused with each step in your career, I would say.
Mhm.
So if you want to be a generalist, I would stop after school and not go to university probably. Um,
Yeah.
if this is something you want to focus on. So for the PhD, I specifically focused on how to characterize these wood materials in order for them to be used in these high performance applications. As we said before, so variability and anisotropy is a big issue or like a big challenge. And therefore, we need to be able to characterize all these materials properly and also without destroying them, of course, because you cannot use it afterwards. in order to put them into this production process, and being pretty sure on the values that you're established or that you determined are actually true and are actually the properties of the material. So I spend a lot of time on different characterization methods. And on a second part, we also talked about this side impact beam, which needs a lot of capacity to take up energy during break. And here we looked into different biomimetic approaches, so taking a look on structures in nature and recreating them for this purpose of high energy consumption. And here we looked at different shell structures, which you can find in the sea. So when you're on holiday and you pick up a shell, basically how these are structured and how these are created, because as you know, they are pretty high. They have pretty high impact strength, I would say, and it's pretty hard to open the shell in case you wanted to.
But I guess this
Mm.
kind of insights that's something that is not unique to the uses of wood, but I guess that could be used on anything basically.
Yeah, and similar to the talk about the advantages or the simplicity of steel, I would say. Also here, a lot of this has been done already, focusing on
Mm.
recreating it using other materials. Yeah. Um,
Mm-hmm.
However, back to the natural material wood, I think the challenges are different. It's not as easy
Yeah.
to process, or it's different to process. I would not necessarily say that other materials are easier to process. It's just different. And when
Yeah.
trying this for the first time, you see that you have new challenges to overcome. So we tried to recreate this using veneers, which worked out pretty well, I would say. So we improved the impact or energy capacity significantly, and it was just nice to see this linkage between stuff you find in nature, and then you try to recreate it using the tools you have at hand. And then you always think, okay, we are so simple compared to nature, and how complex and how efficient nature is creating this stuff, and we are so, I would not
Yeah.
say we are stupid, but it's like we are so far behind of these nice
Yes.
things nature can create by itself. It's always mind-boggling to see this.
Yeah. Yeah, I agree. When you say veneer, Max, and of course we don't have anything near your background in terms of understanding wood and products and everything. But when I talk about veneer, the only thing that pops to my mind is, of course, what's on top of your table and cabinets and so on.
Hmm.
When you say veneer in these constructions, could you try to sort of verbally visualize what exactly that looks like?
Hmm. So basically, when we talk about veneer, the the simplest form of defining this would be it's a sheet of wood that's thinner than 7 millimeters, and everything that fulfills this definition could be considered a veneer. If you
Okay. Okay.
create this by sawing, slicing, or peeling, that would be up to you. As long as it's thinner than this definition, um, you could
Yeah.
also make it a little thicker depending on which standard you look at or which book. But that's roughly the thickness that you have. Um, Now, when
Yeah.
it comes down to this high performance application, the only thing I would say is different is that it's mostly peeled, not sliced, because you don't care so
Okay.
much about the structure that you see on the table, which is
Uh-huh.
easier
Mm.
to dictate by slicing it at different angles. So if you take your stem, for example, slicing it from different sides makes it easier to create a certain structure that is nicely looking, which is most important for the applications you mentioned. Now, when it comes to high performance application, what we would mainly focus on would be peeled veneers. Um, so how would you explain this? Basically, it's like a pencil sharpener, but the full stem, not just at the tip.
Mm.
And here you create a more, so one sheet of veneer or one part of the veneer itself would be more homogeneous compared to the sliced ones. So
Okay.
that would be one advantage. But it's still a multiple millimeter thick veneer sheet. In the case of the high performance applications, I would say they are thinner compared to the other ones because they're more easily formable and you can more easily bend them in different shapes, I would say. Therefore, they
Yeah.
are typically thinner. And then you, so the processing principles then stay the same. You use some kind of adhesive, you press multiple of
Yeah.
these veneers together into the composite you want to have. The advantage for that would be that you can press them together at different angles,
Yeah.
similar to cross-laminated timber, for example, where you have one layer 90 degrees and one layer 0 degrees, and you go on with that. Similar it would be here for the veneers. You can use different angles in order to achieve a certain behavior afterwards, a certain
Yeah.
property mixture. Yeah? So it's rather similar, but there are a few small differences in processing. Yeah.
Yeah. Wow, this is interesting. And just to for me to understand fully, you do that because if you just had a full log of tree that has some performance, but by doing this you can create a performance in the direction you want instead of having that performance. For example, that it's more bendable, thereby can take probably more energy because you can by deformation, absorb some energy, and that's like the idea behind it.
Yeah, so that's one reasoning behind it. And then the second reasoning is again the variability of the properties in the end.
Mm.
So this is valid for using veneers for building constructions as well, for example, is that
Okay.
with the thinner sheets, you have a better distribution of the strength reducing, let's call it defects. Yeah. So you don't
Mm.
have, for example, one knot going from top to bottom all the way through as you would have in a solid wood beam, for example.
Yeah,
But by
makes
slicing it up and putting it in different positions, you have a better distribution of the defects, which makes the material more homogeneous and better predictable again. Yeah. So that would be the
okay.
second reasoning. Yeah.
Mm. That makes sense. How much of an influence on let's say the performance of the engineered wood is also due to the adhesive
Um,
and maybe the way that you do it?
yeah. So I think the adhesive plays a really crucial role um, in regards to the the basic goal to keep the parts together and like transfer loads from one layer to the next. So that would be the basic, similar to how you would define a basic veneer. This would be the task of the adhesive in the first step, I would say. And
Yeah,
then what we saw, for example, for the structure that was inspired by nature, by the shells, we also use the adhesive to specifically create differences in stiffness and strength between the layers. So you have a layer of veneer
mm,
that has high stiffness, and then you have a thin
yeah,
layer of adhesive which has low stiffness, for example. And you can also do the same for high strength, low strength, whatever you want
yeah,
to achieve. And this would basically dictate the failure behavior again. So this would dictate how, for example, a crack would propagate through the composite, like
yeah,
through the layer structure. So this
yeah,
would be one way where the adhesive has a key role on top of just holding the pieces together. Um, I think the second one, where we move into some kind of building applications already, um, but is also valid for the high performance automotive parts, um, is also enabling certain aspects of monitoring. So right now there's a project going on with one of the partner institutes that's also located here in Tulln, which is WoodCAST Plus. It's called Kompetenzzentrum Holz in Germany. or in Austria,
Mm-hmm.
which focuses on using the bond line to make moisture measurements and moisture monitoring in buildings, for example.
Okay.
So they create some kind of conductive bond line that gives you information
Mm-hmm.
about the moisture distribution in the building component, which is really critical in
Yeah.
regards to wood, which is susceptible to changing moisture.
Yeah. Yeah.
So this would be already more advanced uses of adhesives.
Yeah. That's that's really impressive
Yeah,
how
then
much that goes into this.
yeah, just maybe research in the adhesive is just a large part of it also. Yeah.
How much of everything that you described now, Max, is something that you could actually produce in real life manufacturing facilities compared
Mm,
to, this can only be done in a lab thing?
mm. Um, so it would be, I think it would be hard to give you a certain percentage of saying like, okay, 45% and 55% or something. I think one important aspect here would be to mention that the study program that we are also like um, offering here, which I did as well, always has this focus of process control and actual like process technology. So I think one important add-on to the classic material science that other universities also offer is that we keep this, how do we actually produce that, in mind. And
Ah,
even if there is
nice.
certain deviations due to the lab scale of things, there is always this question, okay, how would you produce this in an industrial setting? Is it actually possible
Mhm.
for depending on the use case and depending on the industry you're looking at, for example, is it actually possible to produce this in masses? If it's a mass produced panel, for example, does it make sense that it takes 10 times the amount of time that current processes are taking? It will never be feasible economically, actually.
Mm.
So this is something
Yeah.
that we try to keep in mind here. Um, However, I think the limitations in regards to just taking the solution and putting it in the industry processes is the variability of the materials that we are using. So as it's similar for the steel industry, I would say, and it's similar for other
Mm.
composite industries. You have a certain factory which is designed to specifically process a certain combination of materials. This doesn't mean that
Yeah.
you're not able to adopt this or change this facility to process other materials. And similar, I think it's here. So if you use a different kind of adhesive, if you use a different kind of raw material, might it be a different wood species? I think you
Mhm.
need time to adopt your facility in certain aspects in order to
Yeah.
process this. Um, and this also makes it hard to integrate all of those different ideas into one, because I think just changing up your adhesive, if you talk to an industry person, would already mean this and this and this and this must be
Um,
adopted. And you didn't even mention, okay, and now use a different wood species as well. So um, I think at the core of most of the ideas, there's a certain industrial ability behind it. I'm not sure if that's the correct word. Um,
that makes sense.
yeah. And then there are ideas where it's like, okay, there is not even enough raw material to do that. Um, so we also focus. So that's not my area of expertise, but colleagues here do that, who focus on byproducts of food processing, for example, nutshells or stuff like that. Um,
Uh-huh.
and
Okay.
and then there is this question, okay, how much nutshells are there actually? So while the
Yeah.
the basic principle makes sense, I think it would be hard to base a facility only on this type of raw material. So you would
Yeah.
need to think of, okay, how can you combine it with other ones? So I think while the basic processability is always at the core of thinking as well, especially if you do this bachelor degree, um,
Yeah.
there is always some kind of compromises you take in the lab scale. Yeah.
Okay. So in terms of availability and quality of raw materials, what's the are this changing, or how do you see that?
Um, so do you know the typical answer of a scientist is always that depends?
Rasmus is also a science, so yeah,
Former scientist, at least.
I know.
Yeah.
So maybe that's one of the reasons why you move out of science, but this could also be one of the reasons why you stay into science, because there is so many different questions you might ask afterwards. Um,
Yeah.
so uh, I would say that depends on the location actually,
Okay.
and it depends on the time horizon you want to look at. Um, so you two guys coming from forestry, both of you, I guess.
No forestry at
Or
all. That
No.
electronics.
no, but you work in forestry. Yeah, you said. Now I have it again.
Yeah.
So, but you try to provide a solution for the forestry sector. So, but then you probably already realized that the forestry sector has to think in different time horizons than other wood industry, like other industries, and also other than the wood industry. So yes, raw materials and their availability is changing in certain areas, especially in certain areas of Europe. But the time horizons that we're talking about are 10, 20, 50, and 100 years probably. And
Okay.
depending on which time frame you're looking at, it might be that there will be big changes, and then there might be that there are just incremental changes happening. I mean, what we can say right now is, and this has been in the past as well, that there are always times of high calamities happening in the forestry sector. May that be based on storm occasions or dry periods and bark beetle infestations, for example, so insects. But I think what we are told, at least from the forest side, is that the occasion or the happening of this is increasing, and the severity is increasing as well.
Yeah.
So
Yes.
in the short term, probably you have to be prepared to have higher amounts of these materials coming onto the market compared to previous decades, I would say.
Yeah.
In the long term, as temperatures are changing, we know also from forestry colleagues that not all the wood species are used to all the climates. So I think that's also something that that plays a key role here. So I think depending on where you are, for example in Europe, and how the climate is looking in this certain area in the next decades or years, this will also influence what raw material you will be having in this area. So different wood species, different amount of wood that will be available. So typically, if you would consider higher temperatures, longer dry periods, less water that's available, basically, you will have slower
Yeah.
growth. So from a wood industry perspective, that's geared towards volume most of the time. This will also have an impact here. So you might have raw material available, but it will not be
Yeah.
as plentiful as before, probably, which is in contrast to what might happen right now, that you have times of really high volume available and then you have times of really low volume. So this variability will probably increase. At least that's what the research is saying and what the forest research is telling.
How about with changing temperatures, changing forestry practices, and everything? How much does that actually influence on the raw material, the quality of it?
Mm. So um, regarding the quality term or the quality aspect, I think it's always a question of how you define quality. So this is
Yeah.
something that we learn also as part of the study program, and that what you also can see as part of your research. I think quality can be adopted quite easily. The question would be,
Okay.
with this new definition of quality, are you actually fulfilling the customer's needs? So this would be the final. So basically back to the basic definition of linking these two things together. So yes, in regards of current definitions, I would say quality is potentially decreasing in the next decades. Mainly due to a higher mix of wood species, which is not necessarily a quality aspect, but some parts of the industry are so focused and so geared on one wood species that this will be an issue. Yeah. The second aspect to this quality would be the basic properties of the materials, I would say.
That was what I was thinking.
Yeah. And here, I think if we consider building, for example, building construction, we will have a big challenge ahead of us because considering Central Europe, I would say, the wood species that's dominating is spruce. And that's also the wood species that has a lot of pressure happening, especially in Germany, for example, where they expect to have only 1/3 of the spruce volume available by the end of this century, which is a big decrease, actually. And the problem here, coming back to the properties of the material, is that spruce has an excellent relation between its strength and stiffness and how heavy it is. Coming back to this strength-weight ratio we had in the beginning already. And this was, so the reasoning why we started to focus on just a handful of wood species is also not because of like stupidity. It's because we realized, okay, there is a certain amount of wood species that we can use for these applications, and they are perfectly suitable for that. So this will be a big challenge because the other wood species that, according to literature, will be suitable for the changed climate are not as well balanced in this regard of weight to strength, which is a big issue for constructing a building, for example. How heavy how big your dead load is in a building without putting any people in there, or how high you want to build it. So the weight of your building material has a big influence. Yeah. And here spruce is, I would say spruce is king to certain areas. Yeah.
Okay. Yeah.
So this will be really a big challenge. Yeah.
And also I find that really interesting, the whole, the entire circle of this, that if we can't grow as much spruce, which would be the best material for it, then what is the direction then? We need to either find a way of enabling that we can still produce a lot of spruce, or completely change what are the materials we need then. So that's an interesting challenge, for a global challenge.
So I think this is especially a global challenge because considering the current shooting star as in wood construction with CLT, cross-laminated timber, I think more than 2/3 of the world production are produced in Europe, focusing on Germany and Austria, I would say. And this stuff is shipped all over the world right now. So, and it's so much, so there's always room for improvement, but it's so fleshed out, it's so well balanced already, that this will be a big challenge, especially if you consider that it might not be suitable to do the same process with other wood species, let's say oak or beech, for example, which are right now discussed as being one of the dominating species in Europe by the end of the decade. And oak is not as easily produced. It's not a softwood in the first place, and it's ring porous, so it has a really inhomogeneous structure across its cross section compared to spruce, I would say. I mean, spruce has also big shifts in density from early to late wood, but in general, it's not as easily processed, and especially as the stems are not growing that straight compared to spruce. So this is something where the spruce has big advantages as well. And as far as we are told, or as we know, the second reasoning for that is on top of straight stems, the branches are pretty flat attached to the trunk. So now if you consider how the boards are produced for cross-laminated timber, you cut out most of the knots basically. So most of the branch area. So that means the steeper your branch is, the more of the board you lose because it goes over a longer distance of your board basically, which decreases your resource efficiency, which is a pretty detailed aspect already, but it's like it shows how complex the discussion is. And then the next step would be oak and beech have a way higher density than spruce. So making the same solid panel might not be feasible because it has 1.5 times the weight, basically, which has implications on the construction side as well. If you do the same thing of beech in a solid manner, you need to have special tools to mill this stuff and to connect these pieces together. Because it's more dense. It's not as easy to drill into the denser part than it is on the lighter one. So these are detailed aspects that have implications on that. And then I think coming back to the raw material availability, if we have less raw material available and if the quality is changing, we need to think about how we use or how we process it the most efficient way possible. And here, I think in the past, an issue was, or a part was that the material was, how should I say that, was cheap enough to not care so much about the different processing steps and how much so you're not throwing it away in the wood processing industry, you're just using it for a different use case. So you basically utilize all parts of it. But in the past, most of it was just burnt. It was either further processed into pellets, or if we stay in the wood, branches and stem tops were straightly chipped and burned. So there was not even a try to use it in a material actually. And now looking at cross-laminated timber, for example, so we have all these advantages. But one downside to it is that it uses a lot of materials. So a lot of raw material actually. So in the worst case, I would say that just 1/4 of the raw material actually ends up in the finished panel of cross-laminated timber. And the other 75% are byproducts, which are not wasted, but they are not ending up in the high-value building product. So here we might also open up the thought process to include different processing technologies that are either veneering again, so using veneers, and there are companies out there that produce laminated veneer lumber, for example, or plywood, which is used in buildings. But also moving into particle-based processes. So you probably know oriented strand board, laminated strand lumber, or also coming down to particle board, which uses some parts of the CLT process already. But if you would rank it in regards to performance, I would start from the cross-laminated timber going down to laminated veneer lumber, then the strand-based laminated strand lumber, oriented strand board, and then I would end up with the particle board. So there is a lot of steps or a lot of levels in between that you could use this material for, instead of just wasting it during cross-laminated timber production. So this mixture.
But I guess that part is really important in terms of making sure that we utilize wood in the most efficient way and sustainable way. And then also, I know we briefly discussed this just leading up to this podcast. Also, the use of fibers in all kind of other materials. I know you're not the expert in this field, but I assume some of the byproduct or this residual of everything that we just talked about isn't this part of something that could go into this alternative use of fibers.
So I think this is best summed up by the basic principle that most of I would say the institute itself is always focusing on the material use of natural materials. So as you said, different fibers, this could be straw fibers that are byproducts of agricultural production. This could be flax, hemp, jute, whatever you can think of. And that the aim here would be to use it in a material and not just use it for fuel, like for energy production. Yeah. And I know this is a really difficult topic because with that you start to move into an actual political discussion away from material science, I would say, because it's out of question that we need the energy as well. So it's of course we need that. And actually, if the more efficient we build buildings and the more efficient we use these other fibers, we still need to heat the place. We still need to drive or fuel the cars. So we still need the energy to upkeep all that. And here we start to move into this, okay, should we use these fibers now for a material? And this can be, as I said, as you mentioned, this can be other fibers as well. For biofuels, do we use it in materials? However, I think, and this is, I think, the basic principle behind this goal of the Institute, I would say, and the goal of the colleagues, that nature has spent different amounts of time to synthesize these materials in the first place. So why should we burn it in an instant, basically? And one of the main issues here is that we still try to convince people that burning wood is climate neutral, or burning whatever kind of natural fibers you might think of. If it took 80 years to create this fiber, except for the issue that you still have to cut it down and transport it somewhere, which creates some form of climate impact as well, which per se doesn't make it climate neutral, obviously. But also that the time it took to create these actually is an important aspect to that, I think.
But so also doing my master's and PhD, it's in energy system, and also how do we use energy, and also Denmark is high on renewable because we produce a lot of wind turbines. So that's also this power to X concept. Let's see if we can use power, electrical power from renewables to replace some of these burning, for example. But back then when I studied it, it was also this. So an example, which is this political, how that affects things. So a supermarket the refrigeration system creates a lot of heat, and it does that because how that actually works is that it pulls heat out of the goods. You don't apply, coolness into stuff. You pull heat out of stuff.
Okay.
So, but the supermarket is not allowed to use that heat to heat the supermarket because that is a different way of billing, or I don't know how the exact words for them. So they had to, just release all that heat into the surroundings of. So it's just wasted, and then they needed to buy the heat from the power plant or the wood burning stuff, and that's political. That has nothing to do with what was the best way of doing it. And a lot of research then how if we just used energy more efficient, a bit like the materials, right? A lot of it is just that's how we do it. It's not built on.
Considering
reasoning.
This refrigerator example, is it I would assume it's a constant supply of heat, I would say. So, I mean, one of the aspects to this discussion typically is, with wind turbines and solar, we don't have a constant provision of heat or whatever. I mean, in this case, it's energy that was provided somehow in the first place to pull the heat out. But basically, I mean, I guess in summer it would be a little more intense than in winter. I'm not sure how it is in supermarkets. I don't have the details on that, but it would be a constant supply.
Yeah. Yeah, it somehow is because you like to keep a constant temperature in a supermarket because you need it to be nice for people to be in it. So you
Mm,
keep a constant temperature about 18 degrees or something like that. And that, of course, puts a heat pressure on all the goods. So you need
mm,
to remove much heat from them to keep this. But you might as well put that back in
mhm,
to the supermarket.
mm,
That was not allowed. Of course, you need to when it's summer because you have a heat pressure on the entire building from outside. Then you use more energy, and then you actually produce more heat.
mm,
So it's also a bit the warmer it is outside, the more heat you produce, and that's of course a bit counter uh, intuitive
mm,
in this case. But again, in countries like Northern Europe, it's typically colder than
mm,
18 degrees outside. So most of the year you would actually have a
mhm,
good case of using the energy smarter.
mhm,
And this
mhm,
has also loosened up now. This is not the case anymore. You are now allowed to use the heat generated in different ways. So, but it was just an example again, like with the materials. A lot of things are just from that's how we always did it, and a lot of stuff is about changing policies around stuff.
mm, mm.
So yeah,
I think it.
and I guess in the material part we're still a little bit more early in that compared to the energy sector. Maybe I don't know.
Yeah, I think here it lacks a clear vision and a clear commitment on this policy level again, because I think the
Mm-hmm.
lobbying on from different industries is way different in quality and doesn't represent the importance of these different industry sectors or their impact on society and climate, however you want to frame it. So I think it it's somehow dictated by how influential a lobby is some of the time, not always of course, but some of the time. And I think here the wood industry, I mean, it started to, I would not say get their shit together, but I think it started to improve or see the necessity to do a unified front and a unified lobbying approach, which was also not the case in the past. Um,
Yeah.
which you may like or not, but I think this is how politics are made today. um, and
Yeah.
I think you have to play by this rule. Yeah.
Yeah. Yeah, and I don't know if it's because we just moved into the realm of forestry and wood that we also hear it much more now. It seems like it's much more part of the picture now, the wood industry, than before. Uh,
Yeah, it changed a lot the last 5 years in
yeah,
Denmark. That's probably how it is
Hmm.
also globally, but at least in Denmark, the last 5 years, it's the importance of the forest and the products from the forest I mean, it's grown tremendously.
Mm.
Max, in the beginning, you said a new question popped up or a new topic popped up, and then you're on to the next study. Looking ahead, are there still important or interesting questions that will keep you working as a
Mm.
scientist?
I think this is one of the nice things of this work that with each so in case with my PhD study and with each PhD that I work with, you always end up with more questions than answers after projects. I think that's one of the nice things here. Um,
Yeah.
and moving on from here, I mean, we talked a lot about existing processes and how we could mix them together and how we could shift focus or prepare for higher variabilities. I think on the resource and the raw material side for wood technologies, there is a lot of uh, insights to gain from opening the view from only using the stem of a tree,
Hmm.
which is the raw material for most of the wood industry's processes, to the whole tree itself. And especially with this changing resources, we will see a change in this distribution. So according to literature, we can see that spruce again and most of the softwoods have very low share of branch wood and stem tops, for example, and shifting towards some of the hardwoods, we will probably see an increase from this to up to sometimes 50%, which is really, really a lot, I would say. So preparing for this shift in raw material, not only in regards to how it's shaped, but also how it is built up, coming back to the impressive stuff nature is doing. Preparing for this because it's built different. I mean, it uses the same components, but it's built different in some ways. And preparing for this will be something that's really interesting to move into. And then I think how to combine this stuff together, because I think coming back to the building products, for example, and coming back to the weight of things, I think there will be no way around combining species, combining different material types, depending on the raw material that's available and depending on the performance that is needed. So coming back to spruce will not be gone at all. So it's not that it will not be there anymore. That's not the case, but it will be there in less quantities. So we have to think on not resource efficiency only on the processing side, creating the least amount of byproducts, but also on the material design side on where to use which kind of material. And I think there is a lot of questions there as well. So these will be the two things out of there. And from my PhD time, I think, I'm not sure how it is with your PhD, but there is open questions that have not been followed on since then. And this is something that I have on the desk, and it's always, I do this when I have time, but you never have time. So I finally hope to move into that as well.
Yeah, I finished my PhD in 2016, and for many years I still had the same background picture on my phone, which was some math which I couldn't solve, but I kept it there just to punish myself for never solving it, and maybe solving it sometime, but I never got about doing it. Yeah, it's not there anymore, and this is the first phone that doesn't have it.
And why is it not there anymore? Is it because the project you guys are doing now is more interesting? Are you getting okay?
I got a new phone. It'll be back, someday. But maybe I should leave it for my kids. I've also said that to them because they noticed it on my phone and said, what is this? And I said, that was a problem I never solved. And they keep it, why can't you solve it? And so I'll probably give it to them.
That might be nice.
So I understand what you're saying.
That might be a great heirloom, actually.
Yeah. The pain to give on. Yeah.
You know what? I think maybe it's a good time to end this podcast today. But thank you so much, Max. It was an absolute pleasure having you on. And to be honest, I learned a great deal about everything that you do and the complex structure of wood.
I find it extremely interesting. Just the whole supply chain, how that affects everything and what will happen. I also find it really interesting.
And the way that you ended with highlighting that we also need to use alternative species in the future and everything, I think that's a really important take. So I think that's a nice way to end it.
Yeah, I would also say that's almost just a podcast just talking about alternatives, maybe. So great.
So thank you so much, Max. It was a pleasure.
Thank you guys for having me, and of course I would like to return the invite and do a WoodCAST in time.
Nice.
Thank you guys.
Nice. I don't know how much we can say on.
So as it has to do about wood on all the different aspects, and this might start in forestry and how you like to change the forest landscape. So it will suit quite well, I guess.
Yeah, nice. we are for that one.
Yeah, exactly.
Yeah.
Thank you, guys.
Okay, thank you so much, Max. Take care.
Thank you very much, Max.
Ciao.